I kind of always like to start with a joke. So, like, what do you call it when someone has like absolute faith in artificial intelligence? Naive bias. Right, and that's actually kind of what I want to talk about, because, you know, artificial intelligence, it's amazing, and any lawyer will tell you. So, here's a guy on Twitter, and he's asking for a lawyer. Apparently, there's a story where there's an Irish car insurance company, and what you do when you have a car and you want to figure out how much you're going to pay for car insurance is you're going to press every button to see what affects the pricing. So, typically, like red cars, you pay more money. Turns out, this guy, if he was born on a Sunday, he would pay like $40 a month more than if he was born on a Monday. So we just sort of try all these values out. He made a he did sort of an analysis. And here's a guy sort of asking on Twitter if there's a lawyer who might want to help him out with this. And you can sort of smell sort of the auto-generate feature trick that happened here. Maybe all this stuff went through a giant tree forest, whatever. But this is one of those moments where AI is amazing, but not always in a good way. AI can have this like aura of authority that make people put blind faith, and it sort of leads to this dangerous situation. And my favorite term for this is I like to call this deep oops. But the real pain is when you do deep oops at scale. And like sometimes it really makes me giggle. This was a random screenshot, so I think this is not in production. But this is PayPal's virtual agent. It states that to get started, simply ask me a question. It also mentions that it's still learning, so if it can't help you, it will be directing you to additional resources. Someone says I got scammed, and the reply is, great. And this is one of those moments where you go, okay, this makes me giggle, but there are like definitely moments where it starts getting properly frightening. So this is something that Catherine Jarmel shared. If you're into fairness and that sort of stuff, definitely follow Catherine. She's like kind of like a watchdog, but she's like a great attitude in this sort of stuff, and she really shares interesting content. I believe it was the state of Oklahoma that was sort of doing this. Essentially, it was like an algorithm in charge of deciding how much money you're going to get for your health care, which, you know, important topic. But I'll just read like 2 sentences from like the suit. So during court, the defendant was saying like, hey, you're going to have to trust me that a bunch of smart people determined this is the smart way to do it. And just to mention like a thing that went wrong here, negative changes like a person contracting pneumonia, could counterintuitively lead them to receive fewer help hours because the flowchart-like algorithm would place them in a different category. And if I'm sort of looking at this, I try to sort of understand what is happening here, and the only way that I find that you can sort of describe this is, you know, for sure it's artificial, but this is also stupidity. This is behavior that definitely shows a lack of good sense or judgment. This is the, I believe, Webster definition of what stupidity is. So when I'm looking at sort of these things happening, I think it's a fair sort of description of what I see going on here. And sort of my central thesis in this is, typically there are sort of 2 things that can go horribly wrong with models. The first thing, and it's I think the prime focus that we have in industry now, is that models don't perform well on a metric that people like. Like typically you want the mean squared error to be low. You want the accuracy sort of to be high, and you focus on this one metric and you make sure that that metric is sort of good. But models can also do something that you don't want them to, and I think as an industry we're trying to cross-validate a whole bunch of stuff, and you know that's fair, but maybe we should be performing on the second thing as opposed to the first thing. And what I would like to talk about are just what I think are some remedies, not solutions, to artificial stupidity. One fix is I think we should be predicting less, but we should do it carefully. Another thing that we can do is we can constrain the features that go into the model. This third thing that we can do, which is probably going to be my main interest in the next couple of years, we can constrain the model itself. And the fourth thing we can do is we can actually do modeling again. And then I'm sorry, but I'm going to have to show you something fundamental, which is a bit of a bummer, because there's a very unfortunate truth to everything that we're doing. Okay, but happy thoughts first. So let's predict less. We are all familiar with scikit-learn. Scikit-learn is great. It's a lovely library, and the way that they introduce this concept of a pipeline I think is fantastic. Typically how many of these classification models inside of scikit-learn work is you sort of have like 2 classes, and you know, it's class A if the probability is above 50%, and it's class B if it's below. Fair. But what you can also sort of do is you can say, well, if I'm a little bit more worried about like precision or recall and that sort of thing, you can sort of move the threshold a bit. You can say, hey, I want to be very sure if it's part of class A, or sorry, of class B in this case. So now I need it to be like higher than 90%. And this can be sort of an argument to say, I want to be extra careful when I make this decision. So this is a way for me to sort of assign more certainty to when the classification algorithm does something. If you think about this, what you can then also do is you can sort of say, you know what, maybe like if I want to say it's class A or class B, it has to have like a certain certainty measure, and otherwise I'll just say, I'll add a label which is called won't predict. Because you might be able to say, hey, that's kind of like a proxy that I'm not sure enough if it's either class A or class B. So that might be an excellent moment to say, you know what, I'll just not make the prediction. And the picture sort of usually looks like this. Like between like the array of like 0 to 1, when the class of probability of class A goes down, the probability of class B typically goes up. And what you can sort of do is you can sort of say, okay, so one part of this would be like predict A, one part of this would be predict B, and the stuff that's in the middle is too uncertain, so I'll just call that do not predict. And this is actually not a bad idea. The problem, though, is artificial stupidity is about to happen. And I'll show this with an example data set. And I can imagine it's very counterintuitive, but something dreadfully wrong might be going to happen real soon. So here's just an example data set. This is from the scikit-learn API. You can make a couple of blobs. And this is the data set you can kind of get. And you predict the color. So like, where are the green dots? Where are the red dots? Where are the blue dots? And when you do like an algorithm, in this case it's k nearest neighbor, this is what we used to have, and this is sort of what the algorithm will start to predict. So you can definitely see there's sort of like the area where there's red dots, there's no green dots in there anymore. This is the prediction of the model. Again, this was like the actual data. This is the prediction, so you can clearly see the sort of this decision boundary where it's either one class or another one. And what you can then do is you can say, I'm sort of going to just remove predictions that were, if I wasn't super certain. And in the k nearest neighbor sense, that basically means anything that's sort of near the borderline or like the 3 landmark. Those are sort of moments where I say I won't make a prediction. Because you can sort of argue, hey, I'm more certain there. These are points that I'm certain of. But here comes the trap. This is our starting point. So what I'm about to do in the next slide, these points become black, and I will sort of show you the region and sort of how we make a decision. So this is the original data. And these are just, again, all the points are made black now, but you can sort of see where the alpha value is sort of low. That's where we are uncertain of our prediction. And where we are actually certain of our prediction is where you see sort of the thick red, the thick blue, and the thick green. Now let's zoom out a bit. I think it's insane that the model says I have a very high probability for red in a region where I've not seen any data at all. That's fundamentally insane. And the blue part and the green part as well, we're assigning super high probabilities to regions where we've seen no data at all. Right? This fundamentally feels insane. We should not have any sort of confidence in those regions because we've never seen anything like that. And it's not just k nearest neighbor. Here's what logistic regression will do to the regions, and here's what a random forest will do to the regions. And you can imagine deep learning, also same issue. And here's where sort of the big issue is. The output from predict proba at best is an approximation of probability. It might be a proxy, but it's certainly not a synonym for certainty. It's just a completely different concept. And this is because, and I will argue that this is fundamental, machine learning models are often designed for interpolation, not extrapolation. If you're trying to calculate the mean, you're trying to calculate the value of the middle number. The middle number might be accurate to predict, but it's the numbers on the verges that are more interesting. And to sort of give a suggestion that you're very sure about what you're doing here can actually cause a lot of stuff going wrong. And I was at PyData Poland a while ago, and that was, I think, the best example of this. If you're, I'm not an expert in this, but I've been told that if you're in labor and expecting a child, what they do in the hospital is they sort of give you a hormone to induce the labor. It's supposed to be very helpful. And the research that was done on this, and I could be, the numbers might be a bit wrong, but the essence of it is, the research that determines the amount of hormones that you get was based, I believe, on women between 21 and 25. So, you can sort of make a classification algorithm on this. But to then assume that if you are older, that your hormone sort of system is exactly the same, that's like a really dangerous statement. But this is what the model will probably do. And, this is a medical application. It's kind of important that we get these things right. And I think it would be less of an issue if machine learning models weren't designed to always give a result. There's usually not a mechanism that assigns doubt to an outcome if a decision is made outside of the comfort zone of where you saw your data. But lucky for us, this last part of the problem we can actually fix with a bit of probability glue. And this is, again, I think a cool trick. There should probably be a package for it. So this is the example we had before. So what I could maybe do is maybe just try an outlier classification on this. If there are dots sort of within this realm, then I'm pretty certain I can make a pretty clear statement. But if I do an outlier detection thing beforehand, if it's detected as an outlier, yeah, then I probably should shut up about it and not make any predictions, because that's risky. My favorite way of doing this is use a Gaussian mixture model. Oh, golly, there's so many cool things about it. It's like an actual probability distribution. But essentially what you do is you just fit a Gaussian mixture on X, and then you sort of take the likelihood distribution, determine some sort of threshold or cutoff, and you kind of get something like this. What you end up with is just a sort of region, a couple of points fall outside of it, but only points within this region. These are points that I can sort of consider, and I can sort of say, look, here I'm kind of certain what is happening. Anything outside of that, I should just sort of take a step back and maybe like fall back to like a bit of sort of a good fallback scenario. And I must stress that this idea is like super general, because if I can do this on like something like this, imagine that you have like a neural network. Say you train an autoencoder first, you have the encoder part, your decoder part. When a new sample gets in that latent state, you can also say, look, that's outlier. That's something we've never really seen before. If we detect that, train some Gaussian mixture on like the internal latent state. This is an awesome way, like in general, to detect something like this from happening. And to me, like, this is where stuff gets like super interesting, because I remember like 5 years ago when I sort of got started, you had all these people saying like, oh, rule-based systems, they're going away because machine learning is taking over. And now if I look at stuff that actually sort of goes to production, you kind of get these rule-based systems again, but these rule-based systems will have like ML stuff in it. So there's an X point coming in. If it's an outlier, okay, then fall back to like a fallback scenario. If then the model also assigns like a sort of dubious probability value, okay, this is a different fallback scenario. And only then, maybe, take an action. So you get these sort of rule-based things in here, but you might be able to append them with, you know, some algorithms. And it's a great way to keep things like slightly more interpretable, but also slightly safer. There's less artificial stupidity happening when you design system this way. I think part of the art is just to fail gracefully. Not predicting given uncertainty is a great idea. If you're uncertain about something, like, do something with that uncertainty. And we can even design fallback mechanisms and unit tests in like the situation I had before that will prevent a lot of mistakes. But one thing we should maybe start talking about to our bosses, algorithms merely automate, approximate, and interpolate. It's the extrapolation that is actually kind of dangerous. And I want to focus on this because mere humans with management actually think that our models are actually supplying us with an actual probability. It's in the language that we are using, and this is wrong. I understand that if you go up to your manager and say, "Ooh, it's an approximate proxy," he will sort of think you're poetic. But there is something in the language here that we should sort of be, mindful of. It's our job to care about the production layer, and we should try not to report on an AI miracle until we really understand when and why models will start failing. So, okay, this is a reasonable fix, but there are other things that can go wrong, and there are other things that we might be able to fix as well. I do think predicting less is a good idea. But we can also do step 2 now and maybe sort of constrain the features. Because if you think about it, what we feed the model really matters. I don't know about you, but I don't want my machine learning model to be like a cookie monster. At some point, you maybe want to think about the stuff that you're giving to your model if you want it to show good behavior. And this is kind of a controversial topic, and that's why I kind of want to talk about it. So here's if you take a lot of courses are like this, not everyone, but a lot of online courses or corporate courses, they sort of teach you how to do scikit-learn by demonstrating the scikit-learn pipeline. And the pipeline's great, but what you typically do is, let's say we take the load Boston data set. Boston data set is like the house price. So you got stuff like number of rooms and area of town and whatnot. And then you do standard scaling and linear regression, and then you typically make a chart that looks something like this. And then you use this as an argument to convince yourself that we've done a good thing. There's a good correlation between what we predict and what sort of comes out. We can convince ourselves that the mean absolute error is kind of low. But the issue is, when you present it this way, no one can see the actual issue. And it has to do with the data going in. And I'm not joking about this, but I then figured, let's see what columns there are in the data set. There, hang on to your knickers. One of them is the number of black people that live in your town, which is kind of shocking. And the other one is the lower status of your population. And I don't know about you folks, but I'm having a really hard time coming up with a use case for this data set where these sensitive variables aren't sort of like data laundering pre-existing bias. And I kind of get it. This is one of those sort of example data sets from the 70s, and world used to be different back then, and that's probably how this data set, because it was very famous back then, made its way into scikit-learn. But I think it's super naive to then present this to upper management and say, oh, look, we got a great model. It performs very well. This is extremely naive. You should probably, maybe, do something with the data going into your model if you want your model to have any sort of fairness guarantees. And I do think it's an important topic. There's a trick, though. It's not perfect, but it should help a lot. So before I can apply any sort of tricks here, one thing we probably got to do is just, how do we quantify this unfairness thing, right? Without measuring this, it's going to be hard to say if our trick has any effect. So here's a definition that I like. It's not the only definition, but it's one that we can at least use. Suppose that we have two groups, group A and group B. I could argue that on one level of fairness, we could say, look, if the predictions for group A and the predictions for group B, if they're sort of always the same, if like what group you're in is not a proxy for like a difference in predictions, okay, that's a measure for fairness. If it doesn't matter if you're from group A or B, you're going to get the same prediction, okay, that's relatively okay. So what I can do then is I can take the predictions from my model, and what I can then say is, okay, take everyone from group A, look at the sort of predictions they got, do bootstrap sampling, do the same thing for group B, again do bootstrap sampling, and that the difference between those two sort of distributions, that is, if nothing else, a proxy for fairness. It's sort of one thing that we can add to our model maybe. There's sort of one metric that we can sort of check, hey, are we not sort of biased on sort of sensitive variables? So this is the way that we're going to measure if sort of the trick that we're applying has any effect. And then the first trick that you might do is you might say, okay, we got our metric, how about we just drop these sensitive columns? Just make sure that the algorithm does not use them. And it's, again, not the worst idea, it's, whatever, but we should not fool ourselves in thinking this is enough. Probably, because this is a biased data set in the first place, there's probably going to be like some correlations with the other variables with these sensitive columns as well. So you probably have to spend like a little bit more extra effort in sort of getting this information out. And this is where linear algebra sort of kicks in. So one thing that you can do, and like you can kind of ignore the math, but the idea is if there are like two vectors of data, and you want these two vectors to be like independent of one another, what you can sort of do is you can say, look, if this is the sensitive variable and this is the sort of the other variable, just make sure that they are orthogonal to one another. Make sure that the information they share is 0. It's like a linear algebra trick that you can do. So in this particular example, suppose that this was in the high dimensional plane a column for gender, and this was a other column, say income. You can at some point then say, okay, let's just filter out all the gender information for all the other columns like this, and then we can sort of see what happens. And again, I must argue this is a trick, and I just want to demonstrate what it might do. So let's do the experiment. What I'm going to do is I'm just going to show you the normal situation that I had before. I'm going to show you the situation with the two columns that I think are sensitive that I've dropped. And then I'm doing the same thing, but I'm also filtering out the information of those two columns. I'm going to filter out all the information from the other columns. So what you're going to see, this is again the first model. You're going to see the scatter plot of like what we predicted and what we actually got out. And this is sort of the proxy for the fairness. So this is like the distribution of difference between the two groups. Note, by the way, that this is on a scale from like 10 to 50. And the unfairness here is on a scale to like on average -12. So okay, the unfairness is actually quite significant here. This is what happens when I drop the two columns. The mean squared error is relatively the same, but we actually see that this sort of fairness proxy is a little bit moving more towards 0, but we're not out of the woods yet. Like it's an improvement, but still a lot of overlap. Here's what happens when I filter out the information out of all the other columns. Okay. Still not quite 0, but a whole lot closer. And the interesting thing here is you're also able to see that, okay, when are we making sort of errors in our prediction? Because, the mean squared error really sort of skyrockets here. But one thing you can kind of see, the moments when the unfairness sort of happens, the errors that I'm making in this model, those are for like the lower income sort of areas, which is exactly sort of the information that I'm trying to filter out. And you can kind of measure here that the data set is sort of biased where just if you're probably lower income, you're definitely going to get like a lower house rating. And the fact that the mean squared error goes down, that is a bit unfortunate, because it might feel that you're sort of in this moment now where you can sort of say, dang, I got to sort of pick. It's either more accuracy or it's more fairness. And this is really unfortunate, because I don't exactly expect corporate incentives to align here, to put it lightly. But I will remind you, there's actually a thing that we learned the moment before that we can do now. Because if nothing else, what we can do now is we can take like the highly accurate model, we can take the highly fair model, and when there's a difference between these two models, that's a very good proxy to maybe not make a prediction. And it turns out, we can totally see a pattern here. This is like a pattern you can learn. On the y-axis, you see sort of the skew in fairness, and this is sort of the base prediction. And you can definitely see that there's like one region of points where I might be more comfortable making a prediction, and in most other situations, I can sort of say, right, this is unfair. The model should do like definitely a fallback. A human being needs to look at this. We should not automate this decision. Now, I do want to mention here, this is a trick, this is a tactic. Fairness in general is like a much larger topic. But the thing that's really hard in this space is that fairness typically is in the eye of the beholder. And there's sort of an issue with this, because what I find fair might not be the thing that someone else finds fair. But above this issue, there's an even harder issue. Like, I like the trick I just showed you. I like the fact that the fairness is sort of, like the unfairness thing is definitely sort of going to zero. I think that's a nice thing. But in order to apply this trick to cause fairness with regards to income and skin color, I need to know the income and skin color. If I would not have had these columns in my data set in the first place, as we saw before, there would still be much unfairness in there, and there would be no measure for me to sort of compare. And this might mean that fairness is going to come at the cost of privacy here. So this is, I understand it's kind of like a controversial topic, but I do want to sort of make one argument here. Fairness at the cost of privacy might be a bargain. And let's be cynical here. I would hate for companies to sort of say, we aren't allowed to know your gender, therefore we cannot sort of do this. It will be a shame if stuff like that becomes an excuse to not do fairness. And as we saw before, not including the variable in your model is simply not the same as being fair. It will be like, if we cannot have a metric that can hold people accountable, it's going to be hard for me to come up with a trick maybe to guarantee any form of fairness. And again, that's where the beholder comes in. Important topic, kind of outside of the scope of the day, but there is sort of a trick where we can at least say, look, there's some sensitive variables, I want to correct for that, I want my model not to be a cookie monster, I want my model to be more like a nutritious Elmo. I also want to mention here, just like before, this whole constraining features trick is also potentially useful for deep learning approaches. You sort of do the same trick within a latent space. And, okay, beware the analogies. Like, I don't think analogies actually work all the time in word embeddings. That's a different talk. But for man-woman, we've probably heard of the man-woman, king-queen thing. Well, imagine you then have sort of this direction where you sort of say, okay, that's sort of what man-woman means, and there's like bias in there that we would like to filter out. Same trick. Make it orthogonal, make sure that the information you have in all the other vectors is sort of kept equal. And then maybe man-woman starts pointing to the word embedding that means gender a little bit more. And then maybe king-queen starts looking at the same word embedding maybe for royalty. There are sort of these tricks that you might also be able to apply outside of the scope of like tabular data, but you might be able to do some of this stuff in deep learning models as well. I have some experience with this, not so much yet, but I do think it's a fair thing to sort of keep in mind. The variables that you put into your system and how they are processed, I think, are more defining in the end result than whatever machine learning algorithm you're going to be using after. As far as I'm concerned, I really like seeing modeling pipelines where you explicitly select columns from a data frame. Just taking your X and chucking that into a machine learning model feels very, very inappropriate, especially when stuff like this can be going wrong. Understanding what goes into your model matters, and everybody here should care. If sort of the predictions going out of your model is your responsibility, then so is the data going in. And at this phase, sort of, okay, we can decide not to make a decision. We can also decide to put our model on a diet. But what we can also maybe do is just, pick models where this sort of stuff just comes as a guarantee. And to sort of introduce what I mean by that, my background is in operations research, so the stuff that I typically do is like optimizing systems and that sort of thing. So one common like homework assignment is like, suppose you've got some data set of like returns for a stock. What you can then do is you can say, okay, stock 1 has a certain type of return and stock 2 has a different return. We're going to sort of spend money in such a way that the return is going to be as high as possible. Well, this math system will be really stupid if you didn't have something like, okay, but we shouldn't exceed the budget. We're allowed to make any investments, but we have a certain amount of budget, and we should never really go over that. I also think the system will be kind of silly if you didn't do something like, oh, okay, but a certain allocation has a certain risk. Maybe you want to make sure that we optimize the profit, but subject to that we want to keep the risk at an acceptable level. This calculation will be really, really weird if I didn't have those two constraints. And what I might be able to argue is that we are sometimes designing machine learning models where we're really just doing the maximization. What we might need to be caring more about is that we actually add constraints to our system, to come to a better outcome. This exercise, like with the constraints, yes, the return on your investment is going to be lower, but you simply don't care because it's a more meaningful thing to calculate. And maybe we can start doing this sort of thing in machine learning as well. And there's a couple of constraints, there's many of them, but I'll just discuss 3 here. Some of them are numerically difficult, but 3 constraints that you can already kind of add are monotonicity, fairness, and label guarantees. So what do I mean with monotonicity? Well, there are these systems where at some point you can say, look, if we ever come up with a model where more smoking leads to more health, that's bad. I have enough domain knowledge to say that should never happen. So maybe I should just make a system where I can sort of say, look, this one column with relationship to y should always be strictly negative or strictly positive. in healthcare, you got many of these situations, and definitely the pneumonia thing will be a thing we might be able to catch with this. Turns out, though, there are systems that sort of do this. You can write, for a single variable, you can sort of write the relationship down this way, and this thing is actually already implemented in scikit-learn. It's called isotonic regression, and it's stuff that sort of looks like this. It basically says, okay, you're allowed to sort of go up, but you still have to sort of minimize the square error, and you're never allowed to go down, or vice versa. And you can wonder, when does this matter? Well, there's a bunch of moments. But one of the things that can go wrong is, imagine you've got this outlier. So, you know, I know for certain that people who smoke should be less healthy. But if I were to give this to a random forest, you'd get this. Suboptimal. If you give it to an monotonic regressor, you get this. And you can still do some stuff like outlier removal before you give it to like the proper pipeline. But again, this is one of those guarantees that you can give to your system such that less stupidity happens. And I do think in a lot of cases, we have enough domain knowledge to sort of declare a few of these variables to sort of be, you know, monotonic. And you might be thinking like, gee, are we like limited to simple models? Well, first of all, simple models aren't limited. I'd just like to point that out. And second of all, no, there's actually like really complex models that you might want to use for this. So believe it or not, TensorFlow has this thing called lattice. It allows you to sort of specify that certain things that go into your model are monotonic, decreasing, or increasing. They sort of do some nice numerical tricks, and the idea basically is if you have sort of a latent state where monotonicity comes in, it should also go out, and by doing that, you can guarantee that, you know, these constraints exist. But XGBoost also has this, and this is just a screenshot from their docs. So here's the model where you see that the monotonicity is not enforced, but if you just turn up the flag, boom, it is enforced. So there are actually already lots of systems and models where you sort of got this sort of thing. And I would really love it if people who are just blindly putting stuff into XGBoost to maybe pay attention to this, because potentially you might do a lot of good by doing this. Another thing that we can do, with the fairness thing we had in mind, you might be able to also add a constraint for fairness. Maybe there's a fairness that I want to guarantee based on someone's gender and maybe on someone's race as well. Turns out, if we are considering a linear system, this already exists. There's a paper of it. And there's a bit of an approximation going on here. The idea basically is you look at the decision boundary and you just want to make sure that the distance from like different groups with respect to the distance to the decision boundary is sort of kept at bay. But my colleague, Matthijs Browns, who sits over there, by the way, he actually made an implementation of this. And we could actually show, on like the data set that I showed you before, that if you tweak this coefficient, that we can also sort of guarantee that a certain amount of fairness is kept at bay. Again, it's sort of just only a linear system here, but by changing the coefficient value, we can see that if we are very strict with this coefficient, the fairness goes up and the accuracy sort of goes down a bit. But this will allow you to maybe design systems saying, I want the highest accuracy, but I want my fairness to remain at this level and no worse. I have two other colleagues, Stijn and Henk, and they sort of made a neural variant of this. This is also more popular. You can probably find this on the internet. The idea here is you just make a deep neural network where the first part of your network just tries to predict like the loss, like the accuracy. But then based on this metric, you train a second network that tries to sort of predict the sensitive variables. And if this network is really able to sort of, the adversarial, if it's really, really able to sort of predict things like race and gender, well, then probably your model's not being fair, and you can sort of put that into the loss function as well. And it's actually like a cool GIF, like I'll just let it run once. The idea is you see sort of the distribution between income predictions, and as we're training and training, accuracy sort of goes down a bit, but the probability, sort of fairness satisfaction guarantees, they sort of go up and up and up. And this is sort of a nice way to sort of change the cost function such that, sometimes you care more about accuracy and sometimes you care more about fairness. But this is a way to keep things in balance. Again, designing systems like this are probably systems that have more of a chance to survive, out there without the need of lawyers. The systems where you just throw everything in and churn and you sort of do cross-validation and just do that. Another thing that I think is kind of interesting, and this is definitely sort of in the new domain area, but how about we make constraints for detection? How about there's like a few data points that we have in our data set that we must guarantee that they will predict it correctly? That's also a constraint you can add to a system. And sort of my dreamy use case of this, me and my girlfriend, we sometimes watch Netflix, sometimes on each other's accounts. It would be amazing maybe that instead of Netflix just measuring my data, I, as a user, can also upload a constraint to Netflix. For example, I can say, look, you're giving me this recommendation for this one show, but I just don't want to see it. Imagine now that we can design systems that way. Instead of just learning a cost function, you might be able to actually add constraints. And the way that this sort of stuff feels to me, at least, numerical issues aside, when you think about models this way, a whole new world of modeling just sort of opens up. Instead of overfitting our design concerns to like an AUC or RUC, we can actually sort of design a system by thinking. We actually get to sort of, design things again. It's not just, take your data in such a way that we can chug it into this mixer. It's like, no, let's just do something with this. And the best analogy I kind of have for this is, like when I look for clothing, I try to look for clothing that fits me. When I see a t-shirt that I really like, it's pretty useless unless it fits me. This is also why I think a bespoke suit is better. There's no better Vincent that will fit in this suit, but there is a better suit that will fit this Vincent. And sometimes if I look at some people doing machine learning, it is starting to feel like we're doing this, right? Because this is what one-size-for-all.fit sort of looks like. And I will be making an argument for an attitude, at least, that maybe we should be moving a little bit away from model.fit and maybe a little bit more towards like tailor.model. Because when tailoring a model, there's less unexpected issues. We have the opportunity to design a system that's like actually super articulate. And we can also more easily answer questions about assumptions without resorting to like basic metrics. And there's a common theme to all of this, because if I start thinking about a model this way, then maybe a model is nothing more than like learning from data, times whatever constraints that I have. So just like that bespoke suit, maybe we need to accept that the model.fit is incredibly naive. And maybe we need to maybe do things what people in physics do. What people in physics try to do is they really try to study a system such that they can come up with a very proper model that might be able to explain everything. And I have one final example, and I might go a little bit over time to explain this example, I hope you don't mind, but it's an example that involves chickens. And we have to be careful here, because something incredibly dangerous is about to happen, but I'm going to show you a really cool trick. But also, like, really cool trick, but something dangerous is still going to happen. Sorry about that. It's the real life. So this is the original data set. This is the chick weight data set. It's my favorite data set that I use for trainings, and you're about to learn why. Essentially, there's a couple of chickens that are born, and then they get a different diet. And the idea is, hopefully, we can check, if you get a different diet, you might grow a little bit fatter, and the meat industry is sort of interested in that. Now, what you can then do is you can sort of say, okay, I want to predict the weight of a chicken based on the time and the diet. And one way of sort of doing this is, just make a Walt-Height encoded variable for the diet, and then you can chug it in a pipeline, and then you get a model that sort of looks like this. But this model is just like wrong all over the place. For starters, chickens are born with the same weight. It makes no sense to have like a constant value, and then if you were born on like day 0, you just weigh more. It's completely unsensible. It's totally not how the world works. And if I start thinking about this problem, like, I can actually describe the way the world works, because essentially it's still a linear regression, but I want the beta 0, like the intercept, I want that to be the same for all the chickens. But the slope, that's the thing that's going to be different for every single diet. Oh, and by the way, we also kind of see that the noise increases over time. So maybe that sigma, we can also sort of split that up over like the chickens and the diet. And you put this in PyMC3, which is a precious library. It's always super fun to use, and like something magical happens because you can sort of see that there's this one diet that has like the best effect for growth, and that one diet also, well, there's 2 diets that have the best effect for growth, but one of them has like a much lower variance. So note how this model is way more articulate. I can actually sort of talk to this model, and I get uncertainty bounds, and all that stuff is epic. And I have like perfect explainability. I have what-if questions that I can add, and there's useful hypothesis test. And there might be human bias, but unfortunately, I'm about to show you what will always go wrong in machine learning. There's one giant problem. If you take a look at this data set, you will notice that there are certain chickens who died prematurely. This might be due to the diet. Our model has no way of capturing this until we tell it to. But yeah, I don't want to put a model into production where, dead chickens are sort of a possibility. Bummer. This entire talk I've spent talking about side effects of our models that go unnoticed if we're not careful. But even what I will argue here is the best model, this can really fail if we don't understand the problem that we're solving. We might be building a system that's going to end up producing a whole lot of dead chickens, but there are some remedies. And consider maybe not predicting. I mean, it's a great way to remove risk, but be careful about what you use as a definition for certainty. And consider maybe constraining your features that go into your model. Optimality definitely goes a lot further than mean squared error. Consider models that constrain, because they're great. You can sort of give a guarantee for something you're afraid of. And give this whole PyMC3 and Bayesian systems thinking a try. It's really nice that you can articulate what you want to model. But most importantly, take a step back and think about what you're doing, because we really need to beware of these dead chickens. They are bound to happen, and this is you need to be a human to sort of really figure this stuff out. So with that in mind, maybe natural intelligence isn't such a bad idea. Please grant yourself the creative freedom to understand the problem, because I think this will help you a great deal in designing whatever solution you have. One more thing. I've been talking about a bunch of algorithms and tools in this talk, and very often I've noticed that I sort of talk about some tools and tricks that are very useful, but then on Twitter I sometimes get the reply like, oh, implementing this is still kind of tricky, and I kind of recognize the fact that it's much easier to sort of do these sorts of systems and stuff if there's actually like an open source implementation of it. So I'm very happy to announce that me and Matthijs and a bunch of other colleagues, and like a guy from Brazil, we have this new open source project called Scikit Lego. The idea is it's kind of like an opinionated package, but I've noticed that all of our consultants were sort of implementing the same estimators and transformers and that sort of thing. And at the moment, we actually have an information filter implemented in here that we'd love to get feedback on. The fair classifier, again, made by Matthijs, also in here. And we're kind of hoping that this can be like one of those packages where there's just sometimes this need for like a kind of a weird or quirky transformer, and we kind of have a place where we can put that, and we will make sure that there's like some tests for it and that things can remain clean. I would love for you to sort of play with this. So thanks. And we actually have stickers for this. You can get them at the NumFOCUS stand after. Okay, so I think we're okay-ish on time, or can I do like one more joke?
Go for it.
All right. What do you call a Swiss algorithm? A neutral network. Sorry. There might not be time for questions, or is there?
Oh, we've got lunch next, so...
Right, so I'll be here, ask me anything. If not, have lunch and enjoy the conference.
We can have like one or two questions, but lunch is next, so it's not too important if we,
I'm fully aware that I'm between you folks and lunch, so like if you want to have lunch, it's fine, I'll be here. But enjoy the conference.